Now, starting this hour, we'll finally reach I think the last, depending on whether we have time to do gravity waves or not, but the last sort of part of our discussion where we essentially just have effects of viscosity, just really playing around with the viscous term, right? So we started after, since the beginning of the second quarter, we started discussing what happens when we can completely neglect viscosity. So we had ideal flows, potential flows. Now we discussed boundary layers, what happens really in between. And now we'll just discuss what happens when you can neglect effects of inertia. And there are several reasons why the effect of inertia sometimes can be neglected. And the first reason has to do with the flow geometry. And in particular with unidirectional flows. So let me just write a unidirectional flow. What we are going to assume is the following. X, Y. So this is, I'm back to my standard coordinate system, X, Y, Z. And I'm going to assume that I have only flow in one direction. Is it working again?
Yeah, it's working.
Oh, so what?
I put it up here.
Is it working?
Yeah.
Well, what did I do? What was?
It was out of battery.
It was really out of battery.
Yeah, this time it was really.
Okay. So I will. Is it working now? Okay. So we'll assume that the velocity vector is always pointing in just one direction, right? And we'll take that direction to be x. So if u is my velocity vector, it's not my velocity vector, it's a vector field again. Eh? So I have a velocity vector at every single point in space. I only have a non-zero component in the x direction. So that will be u, and v and w are equal to 0. So we'll assume, and you have that sometimes when you have flow in particular geometries, in confined geometries, so between plates or in a pipe, then sometimes it's very reasonable to assume the flow to be unidirectional. Now, let's look at the simplification of Navier-Stokes when the flow is unidirectional. Of the Navier-Stokes equation. And so the kind of simplification I will do now, again, these are the kind of simplification I would expect you to be able to do. Okay, so let's start with the Navier-Stokes equation. I'm going to write them in Cartesian coordinates. So you can start writing them because I will just I'm just going to do it at once. There you go. Okay. So these are the Navier-Stokes equation in Cartesian coordinates, and the resizing tool is not great. Oh, okay. Okay, I'll just leave it as that. And so let's see what simplification arise in these equations from the fact that we have a unidirectional flow. So first, if we have a unidirectional flow, let's look at the continuity equation. So V, well, let's look at all of these equations, and let me just cross the terms that have a V, because V is equal to 0. So this term comes out, all of these come out, and this is out. Now, what happens because W is equal to 0, so the velocity in the z direction is equal to 0. Then this term comes out. All of these three terms come out, and this term here comes out. All of this, sorry, is also 0, and V here is also 0. So these terms are also 0 because V is equal to 0. Okay? This is when you have a unidirectional flow. Now, there is one more thing that happens, is because the only term I have left in the continuity equation is partial u over partial x is equal to 0. And that makes sense. If your flow is unidirectional, then partial u over partial x has to be equal to 0, which means that u has to be a constant. Right? This is because you're incompressible. So if you are forced to move forward, you cannot deviate, you cannot move to the side because u is equal, because you are unidirectionals, then the velocity cannot change with x, otherwise you would compress the fluid. Right? So that's a direct consequence of incompressibility for unidirectional flow. That's essentially mass conservation for unidirectional flow. Partial u over partial x is equal to 0. Because partial u over partial x is equal to 0, right, the only nonlinear term that you are left with, so the only term in the only inertial term here is also equal to 0, because partial u over partial x is equal to 0. Now, this discussion we've had before, it's a bit the same. If you're forced to move, there are two ways you can accelerate. Right? You can accelerate, so you can feel the effect of inertia if you're changing direction. But think about, acceleration is the time derivative of a vector. So you can either change the magnitude of the vector, which means you're going straight and your velocity increases. But because the flow is incompressible and you are unidirectional, this is not possible. Right? This is equal to 0. And if your flow is unidirectional, then you cannot change directions. So because you are incompressible and you constrain the flow to move in just one direction, then all of the effects of inertia are out. You can no longer accelerate in a straight line, you can no longer change the direction of the flow, so there is no more effects of inertia. So here, if you want, from the equations, when you have unidirectional flows, then there is no effect of inertia. That has to do with the flow geometry. Your Reynolds number may not be small. It may not be equal to 0 or 0.01, right? Usually, up to Reynolds number on the order of 10, 100, 1,000, and you have laminar flows, then the flow is unidirectional, right? The Reynolds number is not small, so in principle you would expect effects of inertia to be relevant or to be present, but if the flow is unidirectional, then because of the flow geometry, there is no effect of inertia, because you cannot change the direction, and because of incompressibility, you cannot change the velocity. Yeah? Okay. So, let's see what happens. Now, let's say for now, I'm going to neglect the body forces. So then if the flow is unidirectional, then I'm left with for the x momentum equation. Well, sorry. Let me first write it. Then partial u, partial x is equal to 0, right? And that means that u is only a function of y and z. So all along the streamwise direction x, your velocity profile doesn't change. It's going to be the same. It's just a function of y and z. In the x momentum equation, I have rho partial u over partial t is equal to minus partial p over partial x plus mu. Now let me do one more simplification, which I forgot. So if partial u over partial x is equal to 0, then the second partial of u with respect to x will also be equal to 0. Right? Partial u partial x is equal to 0 means it's a constant. So if I take the partial of that, then this will also be equal to 0. Right? So that term is also equal to 0. That is because partial u over partial x is equal to 0. So in the x momentum equations, the only terms I have left is mu in the viscous term, second partial of u with respect to y, plus the second partial of u with respect to z. That's in the x direction. In the y direction, I just have that partial p over partial y is equal to 0. This is similar to what we had in boundary layer. That's the same. So you have a flow which is only in one direction. So you don't have pressure gradients across your streamlines, right? And partial p over partial z is equal to 0. So from these two equations, you can deduce that p is only a function of x. So you can also write dp dx. P will only be a function of x. So you can replace the partial derivative by a straight derivative, because p is then a function of only one variable. And so these here will be the equations for a unidirectional flow. Now note again, the important point here is that I don't have any inertial term here. There is no inertial term. I mean, I have an unsteady term, but I don't have a term really due to inertia here. The nonlinear term is gone. And when the linear term is gone, we have some hope to have analytical solutions. Right? As long as the nonlinear term is in there, don't even try to ever integrate Navier-Stokes equation. You won't. Yeah, it's not going to be a success. It's not going to. It's not going to help. Okay. Hold on. There's one more thing which I want to do. Yeah, and note that here, sorry, I lost my, if I take this equation, the x momentum equation, so one note, if you take now the partial over partial x of the x momentum equation, all your variables are independent, x, t, y, z, so you can switch the order of differentiation. So when I take the partial over partial x of this term, I'll get partial over partial x of partial u over partial t. It's the same as partial over partial, partial over partial t of partial u over partial x. The partial u over partial x is equal to 0. That's from the continuity equation, right? And you get that for this term, and for that term, and for this term. So when you take the partial with respect to x of this equation, all of those three terms here disappear, and you get that the second derivative of your pressure with respect to x is equal to 0, which tells you that in fact your pressure gradient has to be a constant. Right? So your pressure is really either 0, it's either linearly increasing with x or linearly decreasing with x. Those are the only options. Right? Is that clear? So your pressure gradient is constant. It's going to be the same in your pipe, or it's going to be the same in your gap if you have a quet flow. So those are the simplifications that you have for unidirectional flows. And now what we'll do is very briefly derive the solution, the known solutions. But most of them we've seen so many times that I'm just going to write the solution, and I'll let you do it one more time for yourself. So the quet flow, which we've seen when we discussed shear and when we first introduced, what a shear stress was and what the stress was due to viscosity, is the flow that you would have if you are simply driving the flow through the motion of one plate. So you have flow in a gap between two parallel plates. I have a lower plate here, and let's say I have an upper plate here, and I'm moving this plate at a certain velocity. So this is u1. And to make it more general, let's assume that the lower plate has a velocity u0, but usually u0 is always equal to 0. Okay? But you could have the flow between two plates which are not moving at the same rate. I'm just writing that because in a typical rheometer, you could have two cylinders rotating and they're both rotating at different velocities. So it's just to make it more general, but usually U0, we're thinking the lower plate is equal to 0. So I'll keep U0 symbolically, but just in everything I will draw, I'm going to assume U0 is equal to 0. This flow we've seen many times. What we have when we assume steady state is that we have a linear velocity profile with a constant rate of shear. So here on top of that, I'm going to find this profile. We'll assume a few things. We'll assume steady state. So I've been moving the plate for long enough that that I've reached a steady state. And we're also assuming that the flow is only due to the motion of the top plate. Right, so let's imagine this top plate here is embedded into the atmosphere, so I also have atmospheric pressure here and atmospheric pressure there. You could imagine a situation where there would be a different pressure on one side and the other. So on top of having flow generated by just the motion of the top plate, you would have flow due to the pressure difference, right? So here we're going to assume that there is no pressure difference between the two. On both sides you have atmospheric pressure, and therefore, what is the pressure gradient going to be? 0. We know that the pressure gradient is a constant, right? Because it's a uniform flow, and if the pressure is the same here and there, and I know the pressure gradient has to be a constant, then I know that the pressure dP dx is going to be 0 all throughout the gap. Right? So we know that we assume the flow is only driven by the motion of the top plate, and therefore dP dx is going to be equal to 0. So let's derive the Couette flow. On the Couette flow, this is so, at this point I trust that all of you would be able to do this really like that. So I won't spend too much time on this. If you go back to the x momentum equation for unidirectional flows, and dP dx is equal to 0, and the flow is unsteady, the only term you have left is the second partial of u with respect to y is equal to 0, to z in that case. Oh, and I'm assuming a 2D planar flow. So then partial u over the second partial of u with respect to z is equal to 0, and when you integrate that, you get the velocity equal to u1 minus u0 divided by d, where d is the gap size. This is your gap size d here, the distance between the two plates, times y plus u0. Okay, so do this. I'm not doing this integration. Do this. If you're not able to do it, then just go really. I'm just trust that you all would be able to do that. Okay, this is the velocity profile where you just integrate this simple. It's an ODE at this point because u is only a function of z. When you integrate it, you get your velocity profile. It's a linear function of z. Sorry, not y. Yeah. Okay. Now, once you have the velocity profile, you could compute the force, right? So this is something you should be able to do. What is the force acting in the x direction on the on the top plate? Right? Do it. Just try. You have the flow velocity field, so you can compute all of these things. Okay, so the Couette flow is a very simple flow. I'm just going to skip really quickly over that. Number 4, the Poiseuille flow. Again, the Poiseuille flow we've seen a few times, but now we can derive it. And we'll derive you could have the Poiseuille flow in a 2D gap. We'll derive the Poiseuille flow in a cylinder. Okay, so flow in a pipe. So let's assume that we have a pipe. I'm putting now the z direction as my axial, in the axial direction, because I will use cylindrical coordinates. So my pipe is here, it has a circular cross section. Okay, and we'll assume the flow to be unidirectional. So let's discuss this flow. First, we'll assume the flow to be unidirectional. So if I have my velocity field and I'm now in cylindrical coordinate, I have u in the radial direction, u in the circumferential direction, and u in the axial direction. So for a unidirectional flow, the radial component and the circumferential component are going to be equal to 0, and I only have the flow in the axial direction. So we'll play with Navier-Stokes equations later, but let's think about scalings, because whenever you have a problem like this, the question would be, for instance, what is the velocity profile? Let's think about the velocity at any given point, and in particular, let's think about the average cross-sectional velocity. So what is the average velocity at any given cross-section? Now let's do a scaling analysis. If you're interested in this average cross-sectional velocity, you have the flow across a pipe. Now this flow is driven by pressure gradient. So let me write P inlet here, P outlet here. Or actually maybe it's easier to just call P outlet minus P inlet delta P. Right? Before you go into that, you're doing a scaling analysis. How do you do this scaling analysis? What do you think U might depend on? Or if you say you want to do a full dimensional analysis of this problem, what are the dimensions, what are the parameters that you have in your problem? Right? So you have U, the average velocity, this is what you're interested in. Then you may have the what? The diameter of the pipe. What else? The density of the fluid, the viscosity, the delta P, because this is driven by delta P, and so we're assuming that the flow is unidirectional. So we actually know that U is not going to depend on the position in X. U is now just a position, is just a function of, in that case, before we had U, it would be a function of Y and Z. So here U is going to just be a function of R and theta. So UZ is going to be a function of R and theta. So the velocity at the inlet is the same, the velocity cross-section, the velocity profile at the inlet will be the same as in the middle of the pipe or at the end of the pipe. So it's going to be related to U. But there's one more dimension that you have to take in. If you're thinking about delta P, then you have to define this delta P is over which length. So the length of your pipe also comes in. Right? Or you take dP over dx, but if you say I have a pressure drop between the inlet and the outlet, then the length of your pipe is going to be important. Yeah? So then you have L. So you have 1, 2, 3, 4, 5, 6 with always the same units, kilogram, meters, and seconds. So you expect 3 non-dimensional parameters. Now there is one which you see directly, right? And this is the Reynolds number. You will have a Reynolds number. Let me write as rho U. In this case I can take D or I could take L. The most relevant one is D because this is the one which will give you a characteristic scale for the shear stress. So rho U D divided by mu, that will be a Reynolds number. This is going to be 1. Another one, because I have two length scale, it will make sense to directly pick the ratio of the length scale as one of your non-dimensional parameters. So P2, I'm going to take as L divided by D, right? And then I have my last one, which is P3. That one will have U, right? And we'll have all kinds of others variables in it, but in particular, I probably want U. I want P3 to be a function of U, to be a function of delta P, right? If it's a function of delta P, it will be a function of L, because delta P is over L, right? And then in principle, I may want it to be a function of R, and of the fluid densities, of mu and of rho, right? Of the material properties. So I want it to be a function of pretty much everything. Now, you know, if the one thing we should note here is the only places. Okay, so hold on. Let me take a step back now. The first observation is that we know from the unidirectional geometry that it's not going to be Reynolds dependent. Now, this is something that we know, right? Because the flow is unidirectional, there is no effect of inertia, right? So you don't expect rho to come in, because rho is a measure of mass, and rho comes in through the inertial term. And if we assume steady state, and we have discussion number one, let's assume steady state. I forgot to say that. If we assume steady state, we know that in our equation we no longer have rho's. Right? Now the Reynolds number might not be equal to 0, but we know the Reynolds number is not going to be important in that case, because we know there is no effect of inertia. When we look at, so now this is our first term, so we know that this one is going to be irrelevant. Right? The Reynolds number is not going to be important when we look at the laminar solution. Eventually when we start looking at turbulence, it will be important. It will become important. But for now, let's say we're looking at laminar solutions, rho doesn't come into play, and so the Reynolds number is not going to be relevant. Now this term here, you know, why do you think is going to be important or not? You know, essentially, when we say we have a unidirectional flow, we're already assuming something dramatic about this number, right? We're essentially saying this number is very, very large, and the flow is only going to be unidirectional if your pipe is much, much longer than the radius. Right? So when we say we have a unidirectional flow, we already say that L, you know, that this number is very large, right? And essentially the fact that it's large goes into the fact that we have a unidirectional flow. So really we just have one dimensional parameters which is left, and this in this unidirectional parameters, when you want to cancel the dimensions, you have to look a bit at the, you have to look a little bit to your dimensions. So I have a velocity, I want to non-dimensionalize it. The only places where I have kilograms is the pressure, mu, and rho. But I know I don't have any inertial terms, so I know I don't want rho into my non-dimensional parameter. Right? So I don't want this rho in there, because there is no effect of inertia, there is no effect of mass. So the only places where I will have kilograms is delta P and mu, so I know I will have a delta P over mu. Now the other thing we should, so let's write that. We're doing a dimensional analysis for what is roughly the velocity. Right? The velocity, do you expect it to increase or decrease with delta P? You expect it to increase with delta P. Right? The larger the pressure drop, the faster the flow, the more volumetric flow rate you will have. So I'll put the delta P here on the numerator. Now if I have a delta P on the numerator, to cancel my kilograms, I already know that I need mu to be on the denominator. Right? And the last thing I need is this delta P. We know from the equation that really is not delta P which is important, but it's the gradient which is important. So what's going to be important is delta P divided by L. So then you know that U is going to scale with 1 over mu, delta P divided by L, and now you need to look at your dimensions. So I'm a bit rushed, so you will see that this number here actually scales with a length scale to the -2. So to finally get a dimensional number, we need a d squared here. Okay, diameter squared or radius squared. Actually, let me put because here I put a radius, but I think then later on in all my notes I put I put a diameter, but I wanted to put a radius. So here d is equal to 2r, okay? And so I'm putting an r here. This is 2r. And so what we expect is to have an average velocity which scales with 1 over mu delta p divided by L r squared. And if we don't get something like that, then most likely we did a mistake in solving the problem. Because I think I would trust more my scaling analysis skills than my PDE solving skills. Okay, now let's derive the Poiseuille flow in a pipe. Okay, so we'll start. Everything is the same as what we did for 2D Cartesian in 2D Cartesian coordinates. But let me put it again, just for the clarity. Okay, so it's just so you see which term cancel. Now I'll do it really quickly. Again, u theta is equal to 0, so all of these terms, everywhere where I see a u theta, I'll put that equal to 0. And ur is equal to 0, so everywhere where I see a ur, I put that equal to 0. This is ur, u theta, ur is equal to 0, and u theta is equal to 0, ur is equal to 0. Now I have partial u over partial z equals to 0. This is the equivalent of partial u over partial x equal to 0 in Cartesian coordinate. Right? So this term here is also equal to 0. So now I'm back to having a uniform, a flow with no inertial term. This is going to be equal to 0 if we assume a steady state, which we will do. And this term here, if partial u over partial z is equal to 0, then partial u over second partial of uz with respect to z is also going to be equal to 0. I'm neglecting the body forces. And I'm assuming the flow to be axisymmetric. And so if the flow is axisymmetric, then uz does not depend on theta. Okay, and so I'm left with these two terms. So we only have the z momentum equation, which is the second partial of p with respect to z. So mu times 1 over r partial over partial r of r times partial uz partial r is going to be equal to partial p over partial z. Now the same manipulation, if I took the partial with respect to z of my z momentum equation, I would get that the second partial of p with respect to z is equal to 0, and therefore partial p over partial z is a constant. It's the same manipulation as before. So I actually know that this partial p over partial z is equal to delta p divided by L. Right? This is from taking partial over partial z of the z momentum equation, of the simplified z momentum equation. Okay. And so this is a constant in particular. So now you see I have, again, if u is only a function of r, I have a second order ODE that I have to integrate. We have to solve this subject to boundary conditions. So what are our boundary conditions? First we have the no slip boundary condition at the wall, right? So r at r equals to r, so this is at the wall. We have that uz is equal to 0. This is our no slip. But now we have a strange thing, which is always a strange thing, and that is because cylindrical coordinates are weird coordinates, right? Because, you know, if I'm moving, you know, this is my cylinder, right? If I'm moving in this direction, if I want to go in this direction, I'm moving in increasing r, and theta is equal to 0. But if I want to move in this direction, I'm also just increasing r, but then theta is equal to pi. So you don't go to negative r's. R is always positive. If you want to go the other direction, you just have to go to theta plus pi, and you increase r again, and this is how you go to the other directions. So you cannot, you know, there is another wall on the other side, and I also want to impose a no-slip boundary condition on the other wall, right? But you cannot do that in cylindrical coordinates because it's sort of a singular coordinate system. But then you have another condition for uz. So then you set your condition at 0, and at 0 you are at the center line, right? You are at the center line, and because you are axisymmetric, you know that your velocity profile is actually symmetric, right? Now this is a condition which sometimes surprises students, but if you think about uz, right, the velocity profile uz as a function of r, right? How do you express that it's actually symmetric, axisymmetric, right? That if I could move to the minus r direction, but you can't in that coordinate system, you know, what would be the condition? That is that partial u over partial z, so partial u over partial r, at r equals 0 is equal to 0, so that you have a 0 slope. Right, that's a symmetry boundary condition. Right? If your derivative with respect to r had a slope at r, then you could not be axisymmetric, right? Because your velocity will be higher on one side than the other. So it needs to be equal to 0. Yeah? And you'll see in the solution that we'll get, and you'll understand why once we have this solution. Okay, I don't have time to do this integration, which is perhaps not such a bad thing. So you integrate in r once, and then you integrate in r twice. And I think you should do it. And you get to the Poiseuille profile. So I'm going to write it here. uz is only a function of r and is equal to minus delta p divided by 4 mu. Sorry, I'm going to write it differently in a way that you recognize more. 1 divided by 4 mu delta p divided by L times capital R squared divided by R squared. Okay, this is the Poiseuille profile. This is a parabolic profile. You see that it depends on the distance to the axis of axis symmetry squared. So if you wanted to represent that, if this is my pipe, right, then this profile looks like this. This is uz, right? Note that here, when r is equal to capital R, if you look at the formula, when r is equal to capital R, what is the velocity equal to? 0, right? So it satisfies the no-slip boundary condition. You also see from this shape here, you could take the derivative, but you also see from this shape that this is a paraboloid, which is centered at r equals 0. Right? So this is our condition here. Right? We imposed that partial u z over partial r was equal to 0 at r equals 0. So we imposed here a flat, we imposed a 0 derivative. You see that if we had not imposed that, if you had a non-zero slope at this point at r equals 0, right? So if my derivative was like this, well, I could not have a symmetric profile. Yeah. So this is how in cylindrical coordinate you actually impose your axis symmetry. So this is the velocity profile. Now, let me just briefly finish off this. So you can compute the volumetric flow rate. So this is the integral over a cross section of uz ds. So it's r dr d theta, right? You should do it as well. Just compute that, and you get q is equal to minus pi divided by 8 times r to the 4 divided by mu delta p over L. Those are all results I would put on my cheat sheet if I were you. That's another that's another way of saying put this on your cheat sheet, right? And so if you want to see what the average velocity would be, then the average velocity is just q divided by pi r squared. So it would be equal to minus 1 divided by 4 mu delta p divided by L r squared. So we do get back our scaling. The only thing we couldn't get from the scaling was the 1/4. Right? So we do have the 1 over mu delta p over L r squared. The only one thing we didn't have is the 1 divided by 4. Actually, from our reasoning, the minus sign, of course, we would have gotten, right? Because if you have a pressure drop, if delta p, you only expect positive u if you have a pressure drop. So the p at the inlet is higher than the p at the outlet. We define delta p as p at the outlet minus p at the inlet. So you expect a positive u when delta p is negative. So then you need this minus sign. Yeah? Okay, I'll see you on Friday. You're right.